Okay, welcome to the DICE seminar, and thanks, Alex, for agreeing to give this virtually. Alex Bullivant is going from Maynooth, is going to tell us about topological orders from centers in 3+1D, and you're familiar with our format, Alex.
Yeah.
So, okay, great.
Thanks for having me. So I've just started at Maynooth last academic year, and so I'm still new to the area. And hopefully once lockdown's over, I'll get to meet a lot more of you face to face. But this hopefully will give you a bit of an introduction to some of the things that I'm thinking about. Okay, so I want to start this talk by talking about topological phases of matter and giving a rough definition. So topological phases of matter are in particular quantum phases of matter, and in particular, by quantum phase of matter, we mean these are physical systems where quantum effects dominate, rather than being thermally dictated, as in the classical phases of matter. And when we think about topological phases of matter, we're always thinking about quantum systems which are gapped, so they have a finite energy gap for the excited states from the ground states, and this maintains into the infinite volume limit or the thermodynamic limit, as well as these theories being local. So the theories generated by local interactions. Now, one concise way of defining what a topological phase of matter is that these are path-connected components in the space of gapped local quantum field theories. Now, what this really means is that, what I really mean by this is that if I take two quantum field theories, two gapped local quantum field theories, I say that they're in the same path-connected component if there exists a continuous family of gapped local quantum field theories connecting them, and these connecting theories are given by varying the parameters of the field theory in a continuous manner. And one of the reasons that this is quite a nice definition of a topological phase is that we can actually enrich this definition in several ways. For instance, we could require our systems to have symmetries and think about paths which maintain such a symmetry, given things like symmetry-enriched topological phases. Okay, now when we think about topological phases of matter, one of the nice properties is that actually we can describe universal or low energy properties of the whole phase.
Sorry, Alex, before you go on, I'm just noting that your definition captures the classical bipartite Ising or bipartite dimer model.
Yeah. So what can happen
does have a continuum limit, which is, and it's purely classical. I'm just observing that the limit of that, the thermodynamic limit of that particular system.
Yeah, is, the thermodynamic limit is the continuous theory.
It is the continuous theory, and it has a parameter. You can have a gapped phase, which is one parameter family of deformations, or many parameter in fact families of deformations.
So
it isn't tight enough for some reason. There's more to it.
Yeah, okay. So I think that I want to pick the parameter for the theory. So I want to pick the parameters for the theory. Then I have a gap. So I could have the gap domain of, so I have the gapped subcomponent of the Ising theory. And so then that would be like, I only consider the gap subspace.
Can I ask a question?
Yeah.
Like Denjo, I'm confused. Suppose I take an ordinary scalar, massive scalar field, 5⁴ interaction, and I vary the coupling constant. I'll get, it's a gapped system, so there will be paths which are connected, which are all gaps. But they are not called topological. So I'm not understanding why you call these topological.
Yeah. So what can happen is that, so I have this family of quantum field theories connected by deforming the parameters of the theory. And then in this slide, what I'm trying to say is that there's some universal properties of this phase, and they're described by a topological quantum field theory. So everything in the same path-connected component, as long as these deformations don't close the energy gap, have the same topological quantum field theory as their kind of long-range infrared effective field theory description. Now, what might happen is that this TQFT could be the trivial one. And so if a system, so we could have a, even though a system is gapped, it may have a trivial topological field theory as its underlying effective field theory. And so these are the ones that we would normally say aren't topological theories.
Okay.
And so it's something about certain classes have interesting underlying TQFT descriptions. And those are the ones that we normally think about as topological phases of matter or topologically ordered systems.
So like Danjo, it is not clear to me why these are quantum.
That's my real point. Yeah, it's not clear to me why I think the definition is satisfied by Euclidean theories, which are purely classical.
So I'm saying that the space I'm considering is purely of quantum field theories. So I'm not taking the space of all field theories. I'm only taking the space of quantum field theories.
But you are not distinguishing between quantum and classical field theories and Euclidean field theories.
This includes Euclidean.
Okay.
If anything, most of the examples are Euclidean. So this definitely includes Euclidean. Everything, all the theories that I'm going to discuss in the following will actually be Euclidean. Okay. Okay, so we have this TQ. So given this description, the universal properties can be described by an underlying or effective topological quantum field theory. And this we can perceive as being the fixed point of the renormalization group action on this path-connected component. Okay, so what do I mean by a TQFT? So I've used this in the previous slide without defining it. And I say that a TQFT, or a topological quantum field theory, is a quantum field theory whose correlation functions are independent of the metric structure of spacetime. And so in particular, the correlation functions remain the same if I take any diffeomorphism of spacetime, even those which break the metric structure. And one of the properties of this definition is that if I take the partition function over a closed spacetime, then the partition function for this manifold is in fact a diffeomorphism invariant. And as in kind of classical phases of matter where we define order parameters, for topological phases of matter, we say that the TQFT is the order parameter, the so-called topological order. Okay. Now, what I think is a nice, what motivates a lot of the remainder of this talk is the following conjecture of Kong and Wen from 2014. And all these numbers are the arXiv numbers. And so what these people conjecture is that topological order in n+1 dimensions, and this will be Euclidean. I'm using n+1 for space-time dimension, even though I really mean Euclidean signature. So in Euclidean signature, n+1D topological orders admit an algebraic description via non-degenerate braided fusion n-1 categories. And so here I'm using a lot of words that I haven't defined thus far. And the next few slides, I want to kind of give a rough idea of what these really words mean. So first I want to talk about, And in the following, we're also going to restrict to the case that n equals 3. So we're going to be interested in 3+1D topological orders and a description in terms of non-degenerate braided fusion 2 categories. Okay, so given this definition or this idea of Kong and Wen, the underlying idea is that this braided fusion 2 category should be a collection of rules. And really, the first point is that there should be a rule which allows me to assign a finite dimensional Hilbert space to the 3-disk, possibly in the presence of so-called massive topological excitations. Now, what I mean by a topological excitation is some excitation of the theory which is measurable at all length scales, and furthermore, its properties are actually protected topologically or non-locally in the theory. In 2+1 dimensions, people often discuss anyons, these particles that carry statistics which are neither bosonic or fermionic, and in the following, we're looking at higher dimensional analogs. Now, the kind of excitations that we expect in 3+1D system, 3+1D topologically ordered systems are so-called particle excitations, but we can also consider so-called loop excitations. So these are like closed string excitations. And we can also have open string excitations where their endpoints terminate on a gapped boundary of the spatial manifold. Now, as well as just defining these Hilbert spaces, our topological order should tell us, so it should define some linear map to diffeomorphism classes of space-time cobordisms with the topology of D4. Okay. Now, as well as just these rules, there's a lot more data to unpack in a so-called Fusion 2 category. And roughly, I want to think about this Fusion 2 category as this bookkeeping device for my physics. And in particular, what it does is using the locality of our topological order, one of the components of my Fusion 2 category is an ability to, given a Hilbert space of excitations in the 3-disk, it provides me with a collection of rules that allow me to decompose this Hilbert space into a bunch of tensor factors. So here we've cut down this Hilbert space into local tensor factors. And the idea is that there'll be some finite collection of elementary tensor factors from which we can build the Hilbert space of any the 3-disk with any excitations just by gluing these together. Now, when it comes to these excitations, not only do we want these Hilbert spaces, but we want their dynamics, how they evolve through time. But whenever I consider a TQFT, it turns out that the time evolution, when I consider some manifold across the interval, or the Hamiltonian, for instance, then this has almost trivial time dynamics. There is no thermalization, there's no time dynamics as such. Instead, the analog of time dynamics is generated by topologically non-trivial space-time evolutions. And the kind that we want to discuss today, well, kind of the most important ones, are so-called motion group representations. So here what I could do is I could imagine having a Hilbert space of the 3-disk with 2 excitations of loops embedded inside. Now, given this Hilbert space, I could imagine a time evolution where these 2 loops pass one through the other. You can imagine the process of blowing smoke rings one through the other. And what happens here is that as these loops evolve through their 4D space-time, they drag out world sheets, generalizing the usual world line of particles. And the amplitude of a process going from the bottom to the top is actually an isotope invariant of this knotted surface embedded in the 4-disk. And so this is where this kind of topological properties of the excitations are being manifest. And it's this idea of these topological dynamics that lead to applications of these systems for topological quantum computing. Okay. Now, in order for us to capture these non-trivial space-time evolutions, we also need to introduce the so-called braiding. This is why we don't just need a braided fusion category, but we need this extra prefix of being braided. And what this braided prefix allows us to do is allows us to discuss some kind of under and over crossings. And in particular, the kind of process that allows us to discuss is we could imagine having our 2 loops. We could decompose their Hilbert space into local tensor factors, and then we could consider a space-time evolution where we start to pass these strings under and over each other. So here I've done a very trivial one where this red string is just slid over the top of this yellow loop excitation. Now, what the braiding allows us to do is it allows us to think about the space-time evolution of this kind of process in a piecewise linear way. So we can break down this kind of knotted surface into local pieces and evaluate the amplitude using these local pieces. And then using some elementary set of these small pieces, we can consider some arbitrary space-time evolution just by gluing these processes together. And so this is really what we're seeing is this braided fusion 2 category is just a way of decomposing these knotted surfaces of world sheets into a combinatorial manner in order to understand the universal properties of a topological phase. Now, one thing that I would like to point out, and I think this is what leads to this being a conjecture, this relationship between topological orders and these braided fusion 2 categories, is that the tension is that in general, we said that these topological phases were gapped quantum systems. And so this is a statement that the energy gap maintains into the infinite limit. Whereas in the following, what we've said that we can actually understand all of the dynamics of this theory just by considering the 3 disk. So there's this issue of the thermodynamic limit. But I'm going to leave that as just a side comment. Okay. So in the previous, we've talked about this notion of n category, and I've really not defined what this is. And so what I want to do now is I want to talk about something called categorification, which is how we arrive at the ideas of categories and n categories, and then how we can generalize ideas that we usually think about in physics and apply them into this n categorical framework. Okay, so roughly speaking, a category is a lot like a directed graph. And in particular, we think about the vertices of this directed graph as being objects of a category. And for each pair of objects, say x and y, we define a set of morphisms. And the morphisms are the set of directed edges which go from, say, x to y. So in the set Hom x, y, I have the arrow A, M, and N, and we call these arrows morphisms. Now, where the 2 structures diverge is that if I'm given a triple of objects, say x, y, and z, we now define what's called a composition function. And what this does is, given a morphism A from x to y and morphism B from y to z, we can now define a new morphism, AB, as their composite, as a new edge going directly from x to z. Now, as with any mathematical structure, these are required to satisfy some axioms. And in particular, the axioms that they're required to satisfy are that the composition of these morphisms is associative. So given 3, it doesn't matter what bracketing I choose. And additionally, we require that for every object x, there is a unique morphism from x to itself called the unit. And the unit satisfies the property that if I go from x to itself along the unit and then along any morphism A from x to y, this is the same as the morphism A from x to y, and likewise with respect to doing A followed by the unit on y. Okay. Now, some examples of categories. Kind of the simplest example is a so-called discrete category. So anytime you're given a set S, we can define a category, the discrete category, to be the category whose objects are just the elements of S and whose morphisms are just the trivial unit associated to each object. And the reason I bring this up is that I think this illustrates that in a lot of ways, we can think about a category as being a set of objects with a collection of relations between the elements. So I can think about a set as being a category where there's no relationship between any of the elements of the set. Now, the kind of categories that we're going to talk about today are so-called module categories. So whenever we're given, say, a finite dimensional K algebra A, we can define a category called mod of A, whose objects are going to be right A modules and whose morphisms will be intertwiners. And the reason I bring this up is that if we consider 2 objects, say rho and sigma, so we have 2 A modules, then the space of intertwiners between them is not just a set, but is a vector space, i.e. a set equipped with additional structure. And so if we have some intertwiner F from rho to sigma and intertwiner G, then of course A times F plus B times G, where A and B are elements of the field, also defines an intertwiner. And in this way, we say that this category mod A is a K-linear category. So a category we call K-linear if its Hom space is a K-vector space. Now, as I said in the beginning, categorification is a collection of ideas where we can generate new mathematical structures by replacing notions involving sets with notions involving categories. And whenever we think about sets, we also need functions. And so whenever we want to apply a notion of functions to categories, we'll now introduce so-called functors. And what a functor is given a pair of categories C and D, a functor is a map from C to D. And in particular, it consists of 2 bits of data. The first is just a function applied to the objects of the categories C and D. So it's a function from the object set of C to the object set of D. And it's a function from the morphisms in C to the morphisms in D. And they satisfy a homomorphism style property. So if I compose F and G and apply the functor, then this is the same as first applying the functor to F, applying the functor to G, and composing them in the category D. Okay. Now, using this idea of categorification, so now what I want to do is introduce an example of categorification given by so-called 2 categories. And the idea here is that a 2 category is a categorified category. So it's in some sense like an induction. So a 2 category now consists of a set of objects, which are the vertices, like in our definition of a category. But now, rather than giving a pair of objects, say X and Y, as having a set of morphisms which connect them, what we now do is we say that for every pair of objects X and Y, we're going to have a category of morphisms between them. And this idea of having a category of morphisms between us allows us to encode kind of higher dimensional data. If a category is somehow like a graph, then a 2 category is like a 2-dimensional generalization of a graph. And so in particular, if we want to think about these hom categories, then what we have is, for given a pair of objects X and Y, we have a category whose objects are going to be arrows from X to Y, and whose morphisms are going to be these 2-dimensional cells who connect a morphism A and a morphism A prime. And we call these 2-dimensional cells 2 morphisms, which is kind of showing their dimensionality. And this composition in this hom category is just the composition of these arrows. So I can think about first traversing the surface A and then traversing the surface A tilde to define a composition role. Now, because we've generalized our hom between every object, we now have a category. Rather than having a composition function, we can now have a composition functor. And the idea here is that this composition functor allows us to define compositions of these cells horizontally. And so what it does is, given a pair of objects in their hom categories, we get a new one from X to Z, and we have a way of composing these horizontal cells. And of course, more generally, we can do this process in an iterative fashion to define strict n categories, which then have an n-dimensional graph-like structure. And often it's thought that you can call sets an example of a 0 category. Okay, but it's not only categories that we can apply the notions of categorification to. When we're studying topological phases, it's really interesting to study categorified versions of algebras. So roughly in the following, I want to think about categorification of a unital finite dimensional algebra. So whenever I have an algebra A, if it's finite dimensional, this is really some finite dimensional vector space equipped with some composition map. And we can also think about things like module theories. So we can have vector spaces with action of our algebra. And like I said before, we can think about the modules of A being arranged to form a category itself. Now, what we can do is, applying this idea of categorification, what we can do is we can define a 2 algebra by first replacing the notion of a vector space with what I want to call a 2 vector space. And a 2 vector space, roughly speaking, is a category equivalent to the category of modules for a separable 1 algebra. A separable 1 algebra is defined like this. But I don't think it matters too much. Now, whenever we had a composition linear map, we can define a composition functor. This is often referred to as a monoidal structure. But we can also define module theories. So we could have a 2-vector space equipped with an action defined by a functor on itself. And now, as well as just having module categories, it turns out that we can arrange in a nice way the module categories of a 2 algebra to form a 2 category. So the module theory of a 2 algebra is in fact a 2 category, and we call this 2 mod of A. But just like how we could iterate the notion of categorification of categories to n categories, we can also iterate this process to form so-called 3 algebras or n algebras, where we first define a notion of 3-vector space. And the way that we do this in an inductive way is that a finite dimensional 3-vector space is really going to be the two category of modules of a 2 algebra. And in particular, we require this 2 algebra to be a separable 2 algebra. The definition of the separable 2 algebra can be found in the citations on the next page. But this is in the sense of which we can keep defining higher and higher algebraic structures, which then capture some kind of higher dimensional geometric structures. And so this is what makes them good for trying to understand physics in higher space-time dimensions. Okay. Now, when I discussed the work of Kong and Wen, I said that they said that a fusion category, we could define n+1D topological orders in terms of so-called fusion categories or fusion n categories. Well, we can now define these in terms of our n+1 algebras. So in particular, a fusion n category is a specific type of n+1 algebra. And in particular, it satisfies a property called fully dualizability. And for details, I suggest the following 2 arXiv articles. But for the purpose of what we're going to discuss now, I think that actually a good defining property of multifusion n categories is the following corollary. In particular, multifusion n categories are what I'm going to define as semi-simple. And this means that when we consider their module theory, all modules are equivalent to some kind of generalized notion of direct sum of simple modules, which is to say that a simple module is a module where there's no non-zero proper submodules. So this is all a bit of a tongue tie. But what I really want to suggest here is that our notion of multifusion n categories is just really an appropriate categorification of a notion of semi-simple algebra. And a lot of the characteristics that we care about when we think about semi-simple algebras lift into this multifusion n category setup. And in particular, a fusion category is a special type of multifusion category where if these were unital algebras, we have the unit of the algebra. These have a unit object, which plays the same role as the unit of the algebra. And this is in particular a simple module. Okay. So having gone through these kind of ideas to give you a flavor of some of the algebraic ideas hiding behind topological orders, how does this relate to the picture of string excitations inside the 3Ds? Well, what we want to do is, in this case, we want to consider multifusion 2 categories. And so this in particular is an example of a 3 algebra. And so what we find is that the underlying idea is that we have a 2 category whose objects are going to be the endpoints of strings terminating on the boundary of the 3 disk. The 1 morphisms of this category are going to be the strings in the bulk of the 3 disk. And the algebraic product is what allows us to put these string excitations side by side. So given some block of this form, the monoidal or this kind of higher algebraic structure allows us to sideways compose these, so-called horizontal composition. And we can glue the composition of 1 morphisms is then gluing these string excitations end to end. And so in some sense, we can decompose, we can see that this notion of multifusion 2 category is exactly what allows us to decompose two loop excitations in the 3-disk into these tensor factors. But we also need to, if we don't describe the physics of these, we also need to discuss the time evolution. And this time evolution is given by two morphisms in this fusion 2 category. But in order for us to describe these kind of topological non-trivial motions, like under and over crossing of these strings, we need to introduce an additional constraint or additional property called braiding on our fusion 2 categories. And the way that I want to introduce this extra structure today is through the notion of a center. And I want to do this in analogy with the center of an algebra. And so I want to begin by recalling. So given an algebra A, its center, Z of A, is the subalgebra of A consisting of elements of A, such that for all A in A times Z is equal to Z times A. So this is the kind of underlying idea of the center of an algebra. And what we can do is this notion of center itself emits a quite nice categorification, which will allow us to understand and kind of classify these motions of these excitations. So this 3 algebra that we were discussing before has this underlying 3 vector space, which is a 2 category, and equipped with a product. So it has a 2 functor or 2 monoidal structure defining a product over this. Now the center of this 3 algebra is what I want to describe as being a commutative sub-3 algebra, or more generally, it could be a class of braided monoidal 2 category. And in particular, if I took my 3 algebra to in fact be a fusion 2 category, I can define its center. And in particular, this will define a non-degenerate braided fusion 2 category, which is equivalent to a 3+1D topological order. And some references that give the formal definitions of the center processor here. But what I want to do in the following is just give a flavor of how this notion of center works. And in particular, I'm just going to describe the objects in the center of A. So A is a 3 algebra. I want to define the objects in this 3 algebra center of A. And we do this as the following. So thinking about the center of a conventional algebra, we have this notion of Z compose X is equal to X compose Z for all X in our algebra. And the way that we categorify this relation is that we say that given the product of Z and X in our 3 algebra, we now define a morphism from Z cross X to X cross Z and a kind of inverse of this. And we call these morphisms half braidings. Now, what we can do is using our picture of our topological phase, we can actually draw these pictures in quite a nice way. So thinking about our 2 categorical presentation of the 3-disk, we could think about some Hilbert spaces. We could think about this morphism as being a Hilbert space of the 3-disk, where we have string excitations of the following form. So the endpoints are on the boundary, and we can think about the following picture. And I think about our inverse as being the same picture, but with the under and over crossings being reversed. Now, not only do we need a half braiding, but we need lots of additional data. And this is why I'm going to discuss part of this. So as well as this half braiding, what we're going to do is we're going to introduce a 2 morphism or a time evolution, which goes from the identity of Z cross X. So we have a morphism from Z times X to itself, which I can visually depict as being 2 string excitations pointing straight up. And we define a time evolution, which goes to the braiding composed of the braiding inverse. And so not only do we need this half braiding, but we need this additional chunk of space-time or world sheet, which allows us to consider the following process. We go from 2 horizontal to 2 with an under and over crossing. Now, additionally, what we want to do is to make sure that this half braiding makes sense is if we're given a morphism question mark, so given any object x, and a morphism from x to x prime inside R3 algebra, what we additionally want to do is make sure that this half braiding is somehow compatible with this. And we make sure it's compatible by saying that if my object z is in the center, if I do a morphism which just acts on x, and so it changes it, and then I do a braiding, then I want some time evolution which changes the ordering of doing the braiding and then this morphism. So we can visualize this as the following. So let question mark, so this morphism we visualize as just being this circle here with the question mark in. We could insert anything we wanted. And so we need a two-morphism, a piece of space-time, that allows us to relate this Hilbert space on the left with a Hilbert space on the right. And an example of this is given by the following. We could imagine some string excitation which has been threaded, which is kind of threading through another loop excitation. And we could imagine, and in the center, we need some form of time evolution, which takes us from a Hilbert space of this form to a Hilbert space of this form. Finally, well, one of the final constraint is that we need a way of composing these half braidings. So if I'm given a half braiding, so if I'm given z, x, and y, I could think about exchanging z and x, and then exchanging z and y to perform an exchange of z and xy. Or I could think about exchanging z with x and y themselves. So I can think about doing this process at the same time. And so we have a two-morphism which relates these two configurations. But the point that I want to make here is that although in some sense this is trivial and it's just some kind of combinatorial data, it doesn't really define a very interesting space-time evolution. What does happen here is that in order to make sure that these kind of knotted surfaces that we're generating satisfy some correct topological, they have to be isotopy invariants, i.e. if we deform these continuously, we should get the same amplitude. What we do is these two morphisms have to satisfy relations of sets. So we have to define an equality of these. And so what this says is that if we think about deforming, whatever way that we deform this picture to this one by using these two morphisms, it doesn't matter what ordering we pick, this defines the same space-time amplitude. And so I get that these are quite confused. In some sense, this is just kind of combinatorial data. But what's nice is that making this writing out this combinatorial data turns out is actually the same as requiring that any combination. So if we take any motion of our excitations, we think about the worldsheet that it defines, these relations themselves are actually enough to guarantee that no matter how we cut this up into elementary pieces, we get the right relations that make sure that this is still an isotopy invariant amplitude. Okay. So what I'm trying to say here is that if we're given some fusion to category C, algebraically, we can define a topological order in the sense of Kong and Wen, in the sense of it being a braided monoidal fusion 2 category that satisfies a non-degeneracy term. Now, what I want to do in the last 10 minutes of this talk is really talk about the physics of these ideas and how can I realize these kind of abstract notions as some concept in a lattice model. And so the way that I want to do this is I want to introduce some class of lattice Hamiltonians. So I want to start off with a result that actually says that if I'm given a multifusion n category or equivalent, this kind of semi-simple n+1 algebra, then I can actually always define a lattice Hamiltonian model which has a non-trivial topological order. And so I'm not going to define in detail, but using the work, so this is proven quite nicely in the work of Gaiotto and Johnson-Fried, and is nicely explained in the work of Yeah. But the idea here is that given this algebraic data, I can define a field configuration of a lattice, and I can define Hamiltonian operators just by knowing this data. And the way that these Hamiltonians are defined is true in all space-time dimensions. And in particular, this algebraic data defines what's called a local mutually commuting Hamiltonian model. So given this data C, we can define our Hamiltonian as a sum of local operators. And so given some spatial manifold equipped with some cellulation or lattice, and here when I say lattice, I really mean some form of maybe not too degenerate CW complex homeomorphic to a manifold. And usually this takes the form of a triangulation. Now, what I can do here is I can define a Hamiltonian where as a sum of operators, each of which takes action in some local disk sub-disk of our spatial manifold. And each of these operators has the property that they're projectors, so they square to themselves, they're idempotent. And given any two disks, say Hi and Hj, then these operators commute with each other. And so this is quite a simple form of Hamiltonian model. But additionally, these models obey one important property that allow us to relate the previous constructions. And in particular, if I take some manifold M equipped with a CW complex.
Sorry, Alex, just out of curiosity, why did you throw in a minus sign in the...
Because I want the ground state to be the +1 eigenstate of these H's. So these H's square to the identity. So they have +1 and 0 as their eigenvalues. And so I want the +1 eigenvalue of these to be the ground state rather than the 0 eigenstate.
Okay.
Okay. And so given a Hamiltonian of this form derived from a multifusion category, we can associate a ground state Hilbert space to a corresponding spatial manifold. But these Hamiltonians have the additional nice property that if I choose some arbitrary cellulation or lattice, then if I have another lattice which only differs by a piecewise linear homeomorphism, then actually these ground state Hilbert spaces are isomorphic. And furthermore, I can define the isomorphism between them in a canonical way. So in some sense, these are Hamiltonian models whose ground state have an invariance under choices of lattices, even though you need a lattice to define them. You can actually define a continuum limit for all of these in a nice way as well. Okay. So given a Hamiltonian model of this form, I now want to consider the 3+1D case. And the following is a conjecture that I'm writing up now and hopefully will be available on arXiv for the next few weeks. And the conjecture is that given a pivotal fusion 2 category C, and this notion of pivotal is defined most nicely in this paper here by Douglas and Reuter. So this is just an additional constraint which makes my fusion 2 category well behaved, and it plays an importance topologically. So given a pivotal fusion 2 category C, we can define the corresponding 3+1D Hamiltonian model of the form I previously described. And in particular, the physics of topological excitations in the 3 disk is exactly captured by the center of C. And so I described previously how it might be the case that we could have this fusion 2 category and its center would have the right properties according to Kong and Wen to define a topological order. What I'm conjecturing is that if I have a class of Hamiltonian models defined in terms of this fusion 2 category, there's a one-to-one mapping between the kind of observables in the 3 disk and the construction of the center. And I'm going to just very briefly outline some of the logic that allows you to make this conclusion. So given the 3 disk, and we have this Hamiltonian here, then the ground state of this Hamiltonian are exactly going to be the states of the 3-disk, which are given by essentially, which are stable or stabilized by the product of these Hamiltonian terms. This is exactly what I was saying to Denja when we were saying that the ground state is the +1 eigenstate of all of these HI operators. Now, using this idea, what we can do is we can use these Hamiltonian operators to define excitations in the theory. So in particular, we say that an excitation is a subregion of D3 or a subcomplex of D3 such that these Hamiltonian constraints go to 0 in a local neighborhood. So for instance, we could have a string coming up through our 3-disk, and we say we can measure the presence of this string by the properties that the Hamiltonian constraints HI have eigenvalues 0 in a local neighborhood of this string. Now, furthermore, what I'm going to do is I want to iterate that actually I want to, when I define this 3-disk, I actually need to make a choice of gapped boundary. When I think about boundary conditions, like when I'm doing classical physics, I have boundary conditions for differential equations. Well, here what I need is I need a boundary quantum field theory for this 3-disk. So I have this Hamiltonian for the 3-disk, and I also need a choice of gapped boundary Hamiltonian terms. And from an algebraic perspective, these gapped boundary terms are defined from the data of our fusion category C, and in particular, they're given by separable pseudo-monoids in C as a technical consideration. Now, what we want to do is we want to classify these topological excitations inside the 3-disk. So how might we do this? Well, the first thing is that we note that our model is gapped, and therefore the correlation function of the theory decays exponentially. And actually for this simple Hamiltonian that we've defined here, the correlation length is actually 0. Now, additionally, what we want to do is we want to say, what are topological excitations? So as I previously said, our topological excitations are going to be those that are measurable at all length scales. And they have this kind of non-local topological style protected properties. Now, using these ideas of it being detectable at all length scale and being correlated, using this idea of measurable at all length scale, our theory having 0 correlation length, it's like having an infinite mass gap. And additionally, and our excitations being subregions, what we can do is we can actually classify our excitations, or these kind of excited regions, via their entanglement with the ground state. And then using this idea, so it turns out that, so because they want to be measurable at all length scales, we can measure them using their entanglement, or we can classify them using their entanglement. And in particular, using the fact that the correlation length is 0, the entanglement between this excited region and this complement is actually localized exactly on a boundary between our excited region and the rest of the ground state. So in some sense, all entanglement is localized on the interface between the excited region and its complement. Now, using this observation, what we can do, what we choose to do, is we choose to cut away our excitation. We cut away this local neighborhood of our excitation, and we replace the data of an excitation with a new boundary, i.e. this kind of internal cylindrical boundary of this 3-disk. Now, using this idea of topological excitations being measurable at all length scales, what we want to do is we want to classify these boundary conditions in order to classify these kind of the entanglement between an excitation and the complement, and thus the excitation itself. And the way that we do this is we introduce a generalization of the tube algebra of Ockenau, which I call a boundary tube algebra. And what the boundary tube algebra is it's a finite dimensional star algebra. And the way that we construct it is given this Hilbert space of our cylinder with our puncture removed, what I could imagine is using this kind of underlying lattice structure, I could imagine gluing a cylinder one inside the other. And so I could imagine forming a bigger 3-disk by gluing these two Hilbert spaces together and applying these Hamiltonian constraints on the gluing interface. And what this does is it projects our theory back into a ground state. So we can use gluing plus applying the Hamiltonian constraints in order to go from a pair of cylinders to a bigger one by composing them together. Now, once we have this, our theories were invariant under the choice of triangulation we chose. And so we can actually use this idea of changing the triangulation or changing the lattice in order to deform this bigger triangulation down into a smaller one. So we have a way of composing two of these kind of annuli across the interval together and forming another one. And so this enriches the Hilbert space of our 3-disk with our excitation removed with the structure of an associative star algebra. Now,
sorry.
Yeah,
What is the meaning of gluing two Hilbert spaces together? What is meant by that?
And so these are local. So these are local Hilbert spaces, right?
What does
we might
that
not be
mean?
able to do this with anything, but we have these local Hilbert spaces. And so what we can do is we can identify degrees of freedom, say on the interior, on this cylinder in the interior, with degrees of freedom on the cylinder on this boundary here. And so we say that if these field configurations on these boundaries coincide, then we can imagine defining a new Hilbert space on the manifold given by the union of these two along this boundary. And so we can define this gluing here. So we can just define a Hilbert space on this new lattice given by the union of the lattice here with the lattice here. And so we can define this notion of gluing in a very topological way. And it's the fact that our Hamiltonian has some topological order, which makes this well behaved. We had some metric field theory underlying all of this. This might not work. It might not be an algebra. It might have other properties. Now, the idea here is that if our excitations are really defined by some boundary condition of this, so this inner cylinder boundary condition, and we want these boundary conditions to be measurable at all length scales, what this process of gluing is really doing is it's like adding more space around our excitation. It's like it takes our excitation, adds more space around it, and then looks at what it looks like after this space has been added. And so in some sense, this is an action of the renormalization group on the degrees of freedom around our excitation. So if we had local excitations, they would be killed off by this process. But because we're considering topological excitations, these properties are invariant under this process. And in fact, what we can do is we define the excitation itself. We can classify its physical properties as being a module for this gluing process. So these boundary conditions defining the excitation are in one-to-one with modules for this algebra of gluing these cylinders one inside the other. Now, this idea, I think, is nicely presented in this paper of mine and Del Camp, but there's other papers that discuss this process. But what's really interesting is that if you take this as just a formal gluing procedure, we can actually recover the whole mathematical structure of the center of C as the representation theory of this algebra. In particular, the data of the endpoints of the string, as defined in this way, define the objects of the center of this fusion category. The modules of this tube algebra are in one-to-one with the one morphisms at the center of C, which we already were kind of interpreting as strings embedded in the 3-disk. And the intertwiners of these modules actually define two morphisms in the center of C. And so what we find is that using this argument, we can actually reconstruct the center of C just by knowing the properties of this gluing algebra and vice versa. If we knew the structure of the center of C, we could then define this Hamiltonian model and define these structures, the corresponding boundary tube algebra. So we have this construction between the two. And I'm missing some steps here, but really the way that we do this is via something called the tube 2 category, which I'm not going to discuss today, which should be thought of as a generalization of Okinawa's tube algebra for those interested. And with that, I want to say that, and so I'd like to end this talk there with this idea of gluing chunks of space together, gives us a way to realize topological orbits.
Okay. Questions? Thanks, Alex.
Hi, Alex. I have a couple of questions.
Yeah.
Hey, John. How's it going?
So I think you have discussed the gapped boundary, but right, not the gapless boundary.
Yeah, it has to be a gapped boundary.
Okay. So the question is the following. So in a 2+1 dimensional topological phase, topological order, we know that there are some boundary states described by conformal field theories, and usually also there is a categorification, if I remember, about CFTs by Siegel. It's not clear to me, so how you would do the same in 3+1 dimension? Is there any way to use category theory to classify CFT in 2+1 dimension, and eventually also to understand the anomalies, because usually these boundary states carry Toft anomaly, global anomalies. Yeah. So is it possible to also encode this information with your approach?
Yeah, so this is something I'm still thinking about.
Okay.
People are thinking about as well. So we have a classification of gapped boundaries in 3+1D. In particular, so what I'm talking about here is the non-chiral models. So I've got some kind of fusion category input. All of the phases that these realize are going to be double topological phases, or double topological orders, right? And so I can construct the space of all gapped boundary conditions from this idea. And so in 2+1D, the gapped boundaries are then going to be module, like often people describe them as being module categories for the fusion category input. And I can define CFTs in terms of this module category style data. But I think it's more common that you see this description of the gapped boundaries. Yeah, I've been struggling to guess at what a 2+1D CFT is from this. But we have a full description of the gapped boundary conditions, and we have some knowledge of gapless boundaries, but I still don't know if it's really a CFT.
Okay. My second question is about fermions, because we know that Wen loves bosons, but actually most of the solid state topological phase of matter are made by fermions. Yeah. Of course, it's hard. I know that it's hard to map your TQFTs with microscopic models, but I was wondering if it's possible at least to add somehow fermionic degrees of freedom by using your category theory, for instance, by using Z2 graded algebra or Grassmannian's valued, forms in such a way, to build some, let's say, spin, spin TQFT, and then eventually find something different. I mean, the braiding, I don't know, something that is more exotic.
Yeah. So the conjecture that I outline here, coupled with the proof technique that I'm using, I haven't checked it, but I am very, very sure that it works for spin TQFTs. And the reason is that because of the way that I've got this proof working in full generality, I can, so there's this work of Gaiotto and Johnson-Fried. And what they do is you can start with a field, i.e. C, and they have a way of promoting a field C into a category, in particular the category of vector spaces. And then via something called suspension. And you can do this again to define 2 vector spaces and 3 vector spaces by the suspension idea. And once you have some n vector space, an object inside it is a topological order. Mm-hmm. Now, what you could have done is you didn't have to start off with C. And so this idea is underpinning everything that I've been talking about today. And so exactly as you said, there's no reason I have to take C. I could, of course, take this like fermionic braided, and the whole story will work identically. It's a little bit trickier, but the lattice models that you construct work exactly the same. The center construction should be the same. And so, yeah, I'm totally happy to work on you with this. Like, it's just takes time to check. But at least mathematically, I'd expect it all to work on the nodes.
Okay, cool. Thanks.
Any other question?
I have a couple of questions.
Yeah.
Oh, Bal.
First is a simple thing. Can you write down an actual quantum field theory showing all this?
Yeah.
What is it?
So we can do this with, so we've done this explicitly with Digraph-Witten theory, which is a lattice field theory, but you should think about this as BF theory. So this is 3+1D BF theory, but with a finite group. Are you aware of BF theory?
Yes.
Yeah. So this is kind of, so BF is defined in all space-time dimensions. And so there's an analog of BF with a finite group. So this is like trivial Lie algebra. It's all trivial bundles.
But
topological.
What does your analysis add to quantum field theory? Experimentally?
What does this experiment like?
I don't know, whatever.
Right. So what we're trying to calculate here is, so you aware of the theory of anyons in 2+1 dimensions. So anyons are particles that exist in 2+1 dimensions. And when you do the exchange statistics, they're not a representation of the spin group of the permutation group, but they're representations of the braid group, right? Now, what we have here is we have the same kind of setup. So when we're talking about these topological string excitations, they satisfy not the braid group, but an analog of the braid group, such as the loop braid group, or there are other groups such as necklace groups.
Okay.
So the experimental parameter is that these topological excitations carry an internal topological Hilbert space, which is protected from local perturbations, but the rotations act when we do braiding. The analog of braiding of loops is you pass one through the other, like blowing a smoke ring, one through the other. And so the experimental observation would be is you produce these loops, say, out of the vacuum. You do some braid experiment where you pass one through the other, and then you bring them together and you see if they annihilate to the vacuum. And this will evaluate to an amplitude, and that amplitude is your experimental observable for these systems.
Can I make a comment? Okay.
Yeah.
What you're talking about are Gaussian groups, okay, from what I see. Okay?
Yeah.
They're from what there's the old paper Goldschmidt, I believe.
Yeah, exactly.
Now we have worked on it, in fact, long ago, and also with Kaufman, we wrote a paper. But even before that, all this is inspired by Friedman and Sorkin, who have discussed mapping class groups of mapping class groups of diffuse of prime manifolds in 3 dimensions. Okay? And they have and the structure of the mapping class group is quite similar to these motion groups. Okay?
It's exactly the same. So a TQFT gives you a finite dimensional Hilbert space for an N manifold.
Yeah.
And that Hilbert space is automatically a representation of the mapping class group of that manifold.
Okay, let me come back to the statement. So what the interest of the mapping class group was that it changed, it was beginning to give exotic spin statistics relationships for the quantum field theory of based on these prime manifolds. So that was a starting point. And there was a paper by, I think, Ian IC was here, of Faye Dowker and Subhati Surya, discussing exactly this influence of the mapping class group on spin statistics. So our paper was again looking at rings. We thought the rings were quite similar, and we knew this Goldschmidt paper. Yeah. So, under the inspiration of these people, we wrote 2 or 3 papers, and we found exotic statistics. Okay? This was 25 or 30 years ago that we did. Okay? So what I don't know from your presentation is all those things were related to the pi1, the flat bundles. the pi1 of the manifold, and that gave all the results that I know. Okay? I don't see what is new being added here. Okay?
Right.
I mean, this language, what does it add besides the looking at the fundamental group and the universal cover, and finding a Hilbert on the universal cover, you find appropriate quotients to get flat bundles on the original manifold. So that gives spinel statistics, motion, the standard notions of spinel statistics, braiding, and so forth. So I don't see what is new here.
So this generalizes this picture. So for instance, we have so in our setting, like for instance, we could have, rather than just being pi1, we could have relative pi2, pi1 comes into this. So we can have two-form curvature, and we can have these generalized homotopy groups acting. It just has to be a pi1 invariant. But for me, the interesting thing is to take a local Hamiltonian model and understand these representations. So we are just calculating these, but what we want to do is we want to calculate them in two different ways, right? So we want to calculate these mapping class group representations for some manifold with these excitations inside, because you can do the mapping class group with boundaries, like you remove the two disk. For anions, you could take the braid group is like the two disk, you remove two disks from the interior. Each of those two disks is like an anion. And you think about the mapping class group. So we want to think about these mapping class groups with subregions defined, like in the Goldsmith paper. But also what we want to do is we want to find some package which unifies all of the mapping class groups in some sense. And so what we want to do is, given any configuration of excitations inside, say, the three disk, so it doesn't just have to be disjoint union of loops, but we could have loops that are like knotted with each other and things like this. And we want to have a unified framework that allows us to calculate the mapping class group representation for motions of, say, knots inside, as well as just disjoint union of loops. And so we want some kind of piecewise linear framework that allows us to answer all of these questions at the same time.
Okay, can I again, sorry, I'm going on say.
Go ahead, Bal. Go.
The first statement is, so far as I know, the unitary representations of the break groups, all of them are not known, okay, from what I know. Okay, already practically, if I want to apply it, and I ask what are the unitary representations of the break group, I can't look up a textbook. It doesn't exist so far as I know. Okay, okay. So I don't know how in representation theory these techniques will help. So just a remark. Second is, you talk about local Hamiltonians. In quantum field theory, the Hamiltonians are never local in the standard sense of algebraic quantum field theory. Okay. So what is the meaning of local Hamiltonians in your context? And the last question is, you talked about some, say, a ball where strings are attached to the boundaries, okay? And going through from one end to the other.
Yeah.
A phenomenon actually occurs, or related phenomena occur in something called bosoms, which Gian Domenico may know. Okay? Bosoms are helium-3. In the one of the phases of, I think, helium-3A, or I think it is the B phase, I am not sure. It happens that there are topological excitations, Mermin discusses them, which are stuck to the boundary. Okay? You can't move them at the boundary, but because of the sticking, there is some topological excitation which is created. I am wondering, maybe you have some application there. This I don't know. I have not thought about it.
Yeah, I don't know.
Coming back to local Hamiltonians, I don't know what they are. Yeah?
Yeah. So here in the back of my head, I'm always thinking about, so I'm thinking about this from the condensed matter perspective. And so when I think about local, what I mean is that if I have some, for me, local is always just that operators have finite support. So I could think about a point on my spatial manifold. I could think about a local neighborhood of this point with the topology of the n disk or the n ball bounding this point, and the parameters of the Hamiltonian only have support inside this local ball. that's the notion of locality that I want to use in this context.
In quantum field theory, the Hamiltonian is not a local operator. I think they call it causal. There is some limit to infinite volumes one can take, called generating causal local operators.
Causal, yeah.
They are definitely, well, there's an integration on the Hamiltonian density. It appears to me that you're talking about the analogues of Hamiltonian densities, which are generally singular objects. Okay?
I think in the back, like, I haven't gone into too much detail because I didn't want to discuss it. But for me, the real definition of locality that I want is one given by the extended topological quantum field theory perspective. And so this is a collection of ideas that, so in the usual path integral context, you know, I could take some space-time and I can take foliations. So I take spatial foliations and I think about some linear map from one foliation to another. And so in some sense, when I take the foliation of space-time, I'm like localizing degrees of freedom on a spatial slice of space-time. Now, in the extended TQFT perspective, what we can do is we can define a notion of locality, which is kind of equivalent to the Lagrangian density, admitting a Lagrangian density. And what this does is I could imagine saying, well, what does my Lagrangian assign to not just a ball of space-time, but what does it assign to a ball of codimension 2 of space-time? So it makes sense to ask these questions of, given some submanifold of space-time, so I have 3D space-time, what could I assign to a point within this? Is there an algebraic data I could assign there? And so this gives a notion of locality, which is the one that I really have in the back of my mind for this, which maybe isn't always the same as the algebraic quantum field theory one.
Okay, thank you. Yeah.
I have one question concerning the first part of your proof.
Yeah.
I think you're starting with a local Hamiltonian system. You want to construct a unique pivotal 2 category up to some isomorphism, perhaps. And have you really achieved that, or are there still some vagueness in the procedure?
So what I have is that, okay. So there's the paper of Douglas and Reuter who give a notion of pivotal fusion 2 category. So this is some kind of idempotent complete monoidal 2 category. And really their definition is like semi-strict 2 category version, but their definition clearly extends to, you could have bi-categories and fully weak monoidal structure. Given this data, I can define a state sum TQFT, like a categorified version of the Torre-Viro Barrett-Westbury invariant. And given that invariant, well, pivotality is what allows me to define that invariant. And then given that invariant, what I could do is I can canonically define this Hamiltonian from the corresponding state sum. And so once I have this state sum, then everything follows through. And so this statement is kind of a Hamiltonian version of saying that in the Torre-Viro theory, what the Torre-Viro fully extended TQFT assigns to the circle is the Drinfeld center of the input pivotal fusion category.
Okay, thank you.
Other questions before? Sorry, maybe I can ask, what I fail to see is what you've been able to calculate that's new here, that if I am given a topological quantum field theory, the data you're taking is taking essentially from that topological field theory, if I understood correctly.
Yeah, so...
Well, I mean, if I give you the path integral formulation of it, I can calculate many other things.
Yeah.
Can you point to something new that you can actually calculate here that's...
Yeah. Well, so what it is that, so given this data of a pivotal fusion 2 category C, this is the data that allows you to calculate the path integral. So this is the same as calculating the path integral. Now, this on its own only allows you to evaluate the path integral on closed manifolds So closed through, like closed, it allows you to calculate it for cobordisms between closed three-dimensional manifolds, is what this data allows you to do here naively. And it doesn't tell you anything a priori what the excitations in the theory are, or in particular how these interact with each other. And so what I managed to do, and so what this work does is, and it could be formulated either in a Lagrangian picture, or I've chosen to formulate it in terms of the Hamiltonian.
But if I'm in a path integral formulation, I know what my topological excitations are. In some sense, I can, if they're Wilson loops, or they're some more general.
So it's a discrete path integral. So it's not a continuum like Lagrangian. So this works for a triangulation of space-time. So you pick a triangulation, you can calculate this, you can calculate the path integral on the discretization, and then eventually you can put it into the continuum limit afterwards, if you so wished. Now, what this means is that you don't have the usual access to Wilson operators and things in this framework. And so it's not a straightforward exercise to calculate this with the sources of matter in that way. And so what this does is this allows me to consider what the excitations are and package them up in a way where I can evaluate I can evaluate a finite set of data, which is these kind of elementary building blocks of data, and I can define any evolution of these excitations via an appropriate algebraic gluing of this data together. So it gives you access to the excitations, and it does so in a way that you can kind of build anything you want out of small pieces.
But is the technology developed to such a stage that you can actually calculate something new, or it's just?
So the technology is very new. So this notion of pivotal fusion 2 category comes from December 2018, and then being able to calculate things like, I don't know of anyone who's calculated. I know there's one example where someone's calculated some data of one example of this. And so this allows me to do this for all examples in a kind of canonical way. But that's the only, before this, there's only one kind of very simple example that had any calculations done.
Can we say that?
What is that example? Sorry, go ahead, Gian.
Oh, sorry. I was thinking, can we say that it's somehow is a sort of topological version of the Regge calculus?
Yeah.
Somehow.
Yeah.
Something to the Regge calculus, right?
Yeah, exactly. So the kind of path integrals that they define is literally Regge calculus, but with like Q deformation, because the Torre-Viro TQFT takes as input a fusion category. So this is the 2+1D version of this, is the Torre-Viro TQFT, which is the Regge calculus at a root of unity, right?
Yeah.
It has a quantum deformation root of unity. So it's like SL2Q or SU2Q level Q version of this. And so this is the 3+1D analog of this setting.
Is it, sorry, can I say something? Or?
Yeah, go ahead, yeah.
Is it fair to say that, like, I mean, here you start with some state sum, and basically, you have some discrete realization of your manifold and the degrees of freedom that live on the various simplices, but then your framework is allowing you to find out, for example, what all the types of excitations in that manifestly topologically invariant theory are, but which live on, let's say, a circle that moves around, a circular string that moves around, and then you can actually calculate amplitudes for any time evolution of these circular strings, not just exchanging with each other, but also merging or splitting in any way that you like, as long as it's still as long as the history is still a good two-dimensional submanifold of the full space-time.
Yeah, that's exactly what this allows you to do.
Right. So that's really an extension of just exchanging a fixed number of rings, for example.
Yeah, that's like so it's like, so you could exchange the rings is an example that you can construct from this data. But the idea is that all exchanges, all bringing these objects together and interacting them as such. All the topological interactions can be.
But here you're able to say, well, I start with no rings, and then I create some rings, and then create one and splits into two rings, and then one of them exchanges with some other ring somewhere else, and they come back, and some of them fuse again, and make some complicated world surface of this thing. And then I can calculate the amplitude for that process actually happening. And then the question is, does anyone actually manage to actually calculate this for any example?
I think that's the key question for me, at least.
Yeah.
And how distant is that? I can imagine doing it in a path integral formulation.
So with this is very close. So I'm working on computing these examples now, even still for some like simple versions. So what we have is that we have a self-consistent collection of data from which in principle you can calculate this. And my next job, once the current paper's been written up, is to actually calculate the amplitudes for some examples.
Okay, any other questions? If not, I think I can stop the recording.
Okay, I have a remark.
Oh, go ahead before I stop. Go ahead.
The motivation for Raphael, Sorkin, and Friedman, and also us to look at these rings, were that they changed the fundamental group of the manifold and changed the braiding properties. So in one very well-known paper, Raphael and John actually proved that this topology in prime 3 manifolds, there are prime 3 manifolds which are such that although it is pure gravity, they can have spin half. Okay? This is very much like Fermions having spin half. So they were motivated very strongly and directly to the physical situation, but then it was found out by them, and that there are these motions which you also showed where one ring passes through the other. There is a mapping element of the mapping class group which moves one of these prime manifolds through the other. Okay? It's a diffeo which can be interpreted that way, and they were causing problems with spin statistics relationship. Okay, that they found. Then the paper of Faye Dowker and Sumati Surya, they looked at cobordism, and they have topology change, which is like your fusion. Okay, so you have a topology change, and here there is no actual physical merging of the 3 prime manifolds. They are simply I think all 3 manifolds are cobordant in 4 dimensions, so far as I know. Okay, and they put some physical restrictions on what can be done and restored the spin statistics relationship. That's a very well-known paper. Okay, so I mean, at least to some of us, I should say. Then we also looked at this motion group of rings, both using BF theory and actually by looking at the fundamental group in very trivial examples, basically Goldschmidt ideas, but it is quite easy to work it out in simple cases. And we found that the spin and the statistics were changed of the rings. So we looked at the universal cover and got results. But we could not do the fusing. We would not know how to fuse 2 rings because we don't have. The way Faye Dowker and Subhati went around it was by looking at cobordism. Okay, I don't have any analog of that. And in quantum field theory, I would not know except by operator product expansions how to merge 2 points. I don't know what it means, okay? Unless one goes into operator product expansions. This is my remark. Okay?
Yeah. We know how to do fusion here because the fusion is kind of like taking tens. We have this kind of topological charges, and the way that you think about the fusion is the fusion is done in a cobordism style way, and the idea is that because these are isotopy classes of motions of these loops, then in some sense I can always nudge my isotopy class of motion such that it is a kind of cobordism. They do fuse as a kind of cobordism style motion, right? There's a kind of, you can think about nudging these to a regular kind of framework. And then here, like the fusion for this is actually not too bad to work out. Once you know that you have this cobordism structure and you nudge them into this cobordism style fusing, how we've defined this stuff in terms of representations style data, that we can define analogs of like the 3J symbols and the Clebsch-Gordon coefficients in order to define the fusion of these objects. So fusion is not too bad. I don't know if that's
Okay.
when it's done. Yeah, we can rewrite it as like a 3J symbol.
Okay.
Okay. Well, let's thank Alex again. I think he's local, so we can quiz him hopefully in person in the future now, and catch up with his calculations. Okay, thanks again, Alex.
Yeah.
I'm going to stop the recording.